The first slide set was mainly on straight development length. And then we said in many cases, it's going to be just much easier if you provide a hook. And the hook can be one of the three. Here are some examples of hooks. You have 180-degree hook. Here's a rebar. Then you bring it. And then, of course, you need to have certain size here. This size is going to be called D. And D here, it says, is going to be equal to 6 times the bar diameter. This is going to be the bar diameter that you're trying here to hook it. If the bar is from number 3 to number 8, and it's going to be 8 dB from number to number, and then you have some guidelines here. This one here, this is what you call here 180-degree hook. This length from this point all the way to here to the end of this tail is going to be about 4 dB, minimum 2.5 inches. This length, this is what we call here LDH. In the previous slide set, we just have LD, development length. And here we're going to call it LDH, development length for hook. It's going to be hook development length. LDH will have a separate equation. It's going to be different from that we use for straight development length. We have another hook here that we call it 9-degree standard hook. So all of this is going to be called here standard hooks. 3 different types, 180, 90-degree, and this one is what we call here 135, which means this piece. Let's give you the 135. This shape here, this is actually what we call cross tie. So if you look in the code, you're going to see a name for this type of ties. We call this cross tie. For the hook, 9 degrees, the straight piece is going to be 12 dB. And this length here is going to be the same LDH. We use the same equation for 9 degree, is going to be the same for 180, is going to be the same for 135. Same equation for the hook. Whether you go with 90, 180, or 135, is going to be exactly the same equation, LDH. So there's no differentiation here when it comes to the code when it comes to 90 versus 180. So at the end of the beam, if I have a rebar like this, now I'd like to get rid of it. Starting at this point, I need to provide LDH. LDH is going to be made from the end of the hook all the way to the point at which you don't really need it at. Here's the equation. It looks much simpler than the previous one. The previous one was kind of a little bit longer, has CB and this kind of things. So this one is going to be a little bit simpler. And my expectation that this LDH is going to be smaller than LD by a lot. Because just think about it this way. In the first mechanism to resist any tension bar that you have in here, let me draw here a small arrow for quick. So you have the tension bar coming this way, tension force is going to be coming this way, you need to resist it. If you have a straight, it's going to be all based on the bond between the concrete and the bar. But in here, you're going to have a little bit of bearing because the concrete is going to be in this location. So when you have concrete here, this hook, this piece, and this piece here is going to be bearing on the concrete. In the straight development, it's going to be all based on the bond. This is the reason that here you are going to have more contribution of the concrete and bearing than that for the straight length. And then it says here in this equation it's going to be 0.02 psi sub E, and I just have here one value or two values for the psi sub E for the epoxy coating, either 1.2 or 1. If you remember in the previous straight development, we have 3 values. So this here is going to be a little bit simpler. So we have 2% of psi sub E, just factor for the epoxy coating, times F sub Y. F sub Y here, it has to be in PSI. Divide times dB, the bar diameter that you're trying here to splice or provide a hook for it. And lambda is going to be 0.75 for lightweight concrete. Otherwise, you just use 1 for normal weight concrete. Divide by square root of V prime C, and also this is going to be in PSI. So let me put here a couple of notes. I'm going to say this is going to be here in PSI. Just be sure that psi in here and in here. At the end, after you're done with your analysis, you need to be sure that this LDH is not going to be smaller than 6 inches. It's not also smaller than 8 times the bar diameter. It's kind of additional condition that they put here for you. I have also some factors. It says here, you have this LDH can multiply by 0.7, which means that you can make it shorter if the rebar size can be number 11 or smaller. When you have the side cover, it's going to be less than 2.5 inches for 9-degree hook. So I see here that CB is going to be also included, but I'm not going to have an equation for it and it doesn't go as a number. If you recall the other one, it has a CB equation. You need to solve for CB and then put it in your equation. And here, you're going to have a multiplier. It says here, when you go to number 5 rebars, which means most of the rebars that we use, if you have a good size cover, right, what's going to happen? You can reduce this LDH. Also, you have this factor of 0.8. And this 0.8 is going to have for 9-degree hook when you have number 11 or smaller. In case with ties, this one you have ties. This is a KTR factor that in the past use is going to be equal to 1.0. We just ignore it. But here it is going to have a value. I have also another factor that says 0.8 for 100-degree hooks, number 11 is smaller. When you have ties or stirrups, perpendicular to the rebar, and the space is going to be less than 3 dB. So I said, okay, this is good. So I'm going to have some reduction if I need to. And then it says here, this A is required by S provided this can be the reduction factor that we use with the straight development length. It doesn't apply here. So it's not really needed. Okay. I'd like to see an example. How can I use this equation? And what's the benefit of having this hook versus the straight development length? In this example, I'm going to start here by looking at this column. This can be like an elevation. Here's a column. So if you like, here's your column. It goes like this. Here's a beam coming to it. Here's the section through it. So it shows here, here's the column. The width of the column looking from this side is going to be only 14 inches. So the column size, as you see here, is going to be 14 inch, which is the same as the beam width by 24 inch. This is going to be the column size, right? Yes, I should be able to remove this red box. I have 3 rebars on the top for some negative moment and 2 rebars at the bottom. My concern about the 3 number 8, like large size rebars. Now this rebars here is coming at the end of the beam. So this here, the end of the beam, and the beam is just extended this way. At this point here, I have the maximum moment. And to get rid of this tension in the bar, which means to develop it to the concrete, I need to provide LD, the straight development length, in both sides. My concern is really about the column size. And the column side here, I need to extend this by LD. My recollection for number 8, it was really like big. It is not like 24 inch. 24 inch is mainly for number 4 and number 5, things like that, maybe number 3, number 4. But when LD for number 8 and also top reinforcing, I'm expecting here a bigger distance. And the problem is physically, I cannot build the beam this way. Unless I come here at the end of the beam and do a kind of an extension of the beam like this, which doesn't look good. I mean, the building ends here. All of a sudden, you're adding a piece to it, right, as extension to this beam to be able to put the rebar. Because my expectation rebar is going to be like this if I need to go with development length. So it doesn't make sense because this is going to be the end of the building. I can't really do this. So I'm going to exercise here, do through this exercise and figure out LD for straight development length. And after that, I'm going to try also LDH. The problem here says determine the anchorage of development length required for tension top rebars. F sub C, F prime C, 3000 psi, normal weight concrete, lambda equals 1. F sub Y, 60,000 psi. Uncoated, number 8, no epoxy. So psi sub B is going to be equal to 1.0. The side cover of the main rebar is going to be 2.5 inches. This is going to be C sub B. It's just given to me. This is just use 2.5 inches. It says here, inspect the use of 180 hook and compare. So in this picture, it shows LD. And they're telling me, why don't you try to use 180 if this is not going to be working with you physically? I'll try that. Now I'm going to solve first for a straight development length. So what I have number 8, top rebars, F prime C 3000, no epoxy, and it's going to be top rebars because it's going to be more than 12 inches, right? From the table, the 4 divided by 30, this constant is going to be 82.2. Top rebars, size up top is going to be 1.3. No epoxy, your psi sub B is going to be 1.0. For the rebar size, number 8 is going to be 1. Normally with concrete, there is no reduction or additional length needed, so it's going to be 1.0. You try here the product of psi sub T times psi sub E. If it is more than 1.7, use 1.7. So I tried that. 1.3 times 1 is going to be 1.3, less than 1.7. Let me just use this value. No cap or no limit needed. C sub B here is going to be equal to 2 inches, as given here in this exercise, give you 2 inches, plus number 4 is going to be additional half an inch, plus half an inch to the center of the rebar. So I'm going to have here 2 plus half is going to be 3 inches. It's going to be the cover to the center. The CB, when you look here about the center to center of this rebar, which means the distance from here to here, this is going to be simple. You do the math for it. And you'll find out that the CB from rebar to a rebar is going to be equal to 2 inches, which is going to be controlling our analysis. By now, you should be able to do this on your own. I don't need really to go through this. It should be clear. We have done a few exercises on this, a few examples. KTR, I just ignore any ties perpendicular to the rebar. I'm going to ignore this, the effect of them. I'm going to take it to 0. Try this factor, CB plus KTR divided by DB. You should have here a cap of 2.5, turn to be 2.0. Now I'm going to go here to my long equation. Here is KD divided by lambda, psi sub T, E, no epoxy, S, small size rebar, or the size factor, and CB plus KTR divided by DB is going to be 2.0. The bar diameter, number 8, is going to be 1 inch. I need 53.4 inches. Here's the problem. This column length is only 24 inch. So from the right side here, I have no problem because the beam is just extended. I can put this 53.4 inches on this side. Problem is going to be what happened inside the column. I need 53 inches. 53 inches means the rebar is going to be like this. It's going to be going out of the beam, meaning I need to build a box like this to extend the beam like this. It doesn't look nice if you're just walking the street and you see a piece that sticks out like this. So what we are going to be trying here to do, instead of using this development length, is to provide 180-degree hook. So what I need to do is to go back to this equation, right? And try the hook development length. And if turned to be less than 24 inches, right? If LDH is going to be less than 24 inches, I'm going to say this is good. Let me use 180 degrees or maybe 9 degrees. Here's the equation for the 180 degrees. LDH 0.02 times psi sub E no epoxy is going to be 1.0. F sub Y also in psi 60,000. 1 square root of 3,000 psi times 1, which is number 8. I need 21.9. You can see this very close here from 24 inch. So I have here some factors that I can use. The first one is going to be this modification factor of the ACI 0.7, and it says when you have number 11 or smaller, and the side cover is going to be more than or equal to 2.5 inches, which we have. Do we have this 2.5 inches? Let me look. Do I have 2.5 inches? Yes? Help? Can someone help me here?
No,
Yes?
no, it's only 2 inch.
All right. So I cannot use it, right? Can I use this or I cannot? It says here modification factor, side cover 2.5 inch. I need to study this so we understand what this mean by the cover. This cover here is to the tie. It is not the cover to the rebar. But if you look here closely, this is going to be the tie size. It's going to be 0.5 inch, right? And the cover that we have to the bar that we are trying to hook is going to be actually 2.5 inches. So it is 2 inch to the tie itself. But from the bar itself, face of the bar to the edge is going to be 2.5 inches. So actually we have it. We have this 2.5 inches because this factor here is about, if you look here, about the cover to what? To the rebar that you're trying to hook or develop. So I should be able to use this 0.7 factor. The way that you use it is going to be multiplier times LDH. You simply take 21.9, which means this number, right? The one based on this equation, and you just use it, right? Multiply by the 0.7, the reduction factor. Now I need 15.33. I said, okay, let me use 16 or 17 or maybe 18. I shouldn't have a problem here. Would that fit within the column? Now let's look at the picture. From this side, I'm going to be leaving here 2.5 inches. So you have 24. You subtract here 2.5 inch is going to be 21.5. So the available length for LDH is 21.5. So this one in reality is again 21.5, right? Is it 21.5? Are you guys following me? Yes. Am I clear where is this number coming from?
Yes.
24 subtracting 2 is going to be 22, subtracting additional half. So this is going to be available as 21.5 inches. I'm going to see here available. What I need here is only 15.33, which means good. I will provide 21.5. It is true that all what I need is only 15.33, but this is fine because I don't want to come here on my drawings in the detail and show this, let's say, to be exactly 16 inch. I would just simply ask him to extend the bar all the way to the end of the beam. So I should be fine. That is a good option, better than having a piece that sticks out because the development length of the rebar. Any questions? Questions? Yes? Continue. All right. Now the splice, the second section of our business here. The splice is going to happen only for a straight development length. So when you have two rebars, you splice them next to each other, and with that you get the lap splice. You don't do that with a hook. So this lap length is just that simple. That's going to be equal to 1.3 times development length. So what you need to do is to use the long equation. Let me go back to it. You're going to be using this equation. At the end, just multiply by 1.3. So it's going to be the same equation. You're going to have 30% additional to transfer the load from one rebar to the other rebar. Also, the minimum tension lap splice is going to be here 12 inches. I said, okay, good. I have one example. I have simply span like beam uniformly loaded, and it needs number 7 rebars for tension. Effective depth is going to be 18 inch. Now I need to figure out where to stop the rebar. The S required is going to be the same as the S needed. And I have the strength of the concrete and the steel yield strength. Let me show you the picture. Here's the beam. The beam span is 24 feet. Look at this. The beam span is 24 feet from center support to center support. It is uniformly loaded, which means the moment here is going to be W squared divided by 8. Positive moment, which means tension at the bottom. Maximum moment is going to be right here at the middle, which means at 12 feet from one end. If I may do this, I'm going to say the length from here to there, it is going to be 12 feet. 1/2 of it. This beam here requires how many rebars? It says here 6, number 7. So I have 1, 2, 3, 4, 5, 6. And it says AS needed is going to be the same as AS provided. Meaning phi mn is equal to M sub U. When the amount of reinforcing you need is exactly the same as the amount you provided, it means M sub U is equal to phi mn. Does it make sense? Yes? No? Okay. Here's the moment diagram. Moment diagram goes this way. Maximum moment happens here. This diagram is for, if I may say it here, I say this one here represents the demand. Meaning M sub U. This curve for the demand. If you want to see the moment here, it's going to be this much. Moment here is going to be this much. Moment here is going to be this much. Because the demand is the same as the capacity, right in the middle here, M sub U is going to be equal to phi mn. So this one here is going to be M sub U, and phi mn is going to be exactly the same. But if I decide here to keep all of the 3 bars straight from the beginning to the end, I'm going to say my capacity is going to be equal to this phi mn from the beginning to the end. It's going to be just one value. So it's going to say, can we throw some number? I'm going to say yes. Okay. 300 kfoot is your maximum demand. So this value here is going to be 300 kfoot. Correct? This value here. I'm going to say, how about the strength? I'm going to say strength is going to be also 300 kfoot. But it's going to be the same from the beginning to the end because I'm going to be keeping all rebars from the beginning to the end. From this point to that point, I'm going to have this rebar. Meaning that the capacity diagram is going to look like this. And I should be able to call this to be phi mn. This is going to be this guy here. So if I kept all the 6 rebars from the beginning to the end, I'm going to have a capacity of 300 foot throughout the entire beam length. And the moment demand is going to be only maximum equal to 300 foot at only one point. When you go here, this side, it drops down. When you go here, this side, it drops down. And the equation with which we're using this curve here is going to be like this. W squared divided by 8. It's going to be second degree parabola here. The question is, do you really need to keep all of this 6 rebar from the beginning to the end? Can you save some rebars? So the question is, right here, I cannot really use 4 rebars. But right here, maybe somewhere here, I don't really need all of that. So I should be able to drop down the capacity. The way that you do this, you look here at the 6 rebars and then say, maybe at one point I can stop a couple of rebars. I'm going to say which rebars that you can stop. I'm going to say maybe this one and maybe this one. Just stop this through the rebars. Cross them out. We're at. Can I stop this 2 rebars here in the middle? You can say no, because in the middle, I need actually 6 rebars. And this is the reason that I'm going to divide this moment capacity and moment demand into 6 sections or segments. Each one of them represents a bar. As if the first rebar is resisting the moment from here to there. This amount of moment is resisted by just 1 rebar. So this 6 equal segments, each one of them refers to 1 rebar in the moment. If I have here 300 kfoot divided by 6 is how much? Someone help me here? Yes? Is anyone there? 300 kfoot supported by 6 rebars. How much each rebar is resisting or providing as a strength?
50.
50. All right, let's say good. 50 kfoot. So each one of these rebars is just simply resisting, right? 50 kfoot. 50, 50 all the way to this number here. So what I'm thinking about, why don't I stop 2 rebars from here and just keep the strength to be about here? And say, but I cannot do this here, right? I need to start from this point, right? So I'm saying at least I need to keep 6 rebars for this distance from this point to that point, which we call here x1. Now I need to understand this x1 and y1. What does it mean by that, right? This y is a 300 kfoot. So I understand that. It makes sense. The total capacity. Y2 is going to be 100, correct? Y1 is going to be 100. Y2 is going to be 200. So I should come here and say this Y2 is going to be 200 kfoot. And this is going to be capacity of 4 rebars, 1, 2, 3, 4. And this Y1 is going to be only 100. I'm just throwing the number here, 100 and 200, just to make it easy to understand. So actually, right here at this point, right here at this location, I should be able to use only 4 rebars because my demand becomes in here, from here to here, is going to be 200. And I should work with the capacity, right? So that this is going to be my capacity line. It's going to be like this. If this makes sense to you. So my capacity line is going to be like this. And from here, it's going to be like this. So actually, when it comes to the rebars themselves, I'm going to keep 2 rebars from the beginning to the end. If this makes sense to you. Additional 2 rebars, the beginning to the end. And then 2 rebars only from here to there. We call this curtail of the rebars. We start to cut the rebars down. If I don't need it, I'm not going to provide it. Does it make sense? Yeah? No? Furthermore, I can cut it down like this. I can do something like this. So here's the first two rebars. When it comes to the actual rebars, I can run it from this point to that point. The second set of rebars, which means there's two rebars, I can just make them short like this. And the last two rebars, I'm going to keep them from the beginning to the end. So your capacity diagram, it's not going to look like this. It's going to be actually like this. I'm just using here 1/2, and whatever happens in this half, you can copy to the other half. So in here, between this point, the center, to that point, I'm going to have here 6 rebars. And then from here to there is going to be only 4 rebars. From here to there is going to be only 2 rebars. And with that, I should be fine, because use the capacity is going to be a kind of the envelope of the demand. Now, how would you find out X1? How about X2? How do you do it? Do you really need the actual values for the moment and things like this? I'm going to say no. Because I know that this height here, this Y1, is going to be equal to 1/3 of the big Y, uppercase. And this Y2 is going to be 2/3 of this big Y. I know also the equation is going to be second degree parabola. Let me just jump to this slide. I'm going to go back again and explain it a little bit more. Because it's here second degree parabola, I can say that X1 divided by this distance, 12 feet. X1 divided by 12, as you see here, X divided by 12 squared is going to be equal to Y1 divided by the big Y. This Y1 divided by the big Y is going to be equal to 1/3, as if this is going to be like 6 rebars, represented by 6 rebars, and this one represented by 2 rebars. Let's say 2 divided by 6 is going to be 1/3. For that, this X1 is going to be equal about 7 feet. So I said, okay, this is going to be 693, about 7 feet, which means it's this. So good. Can I just stop the rebar here? Is this enough? Is this what the code says? 2 rebars going to be only from here to there. Code says no. You need to extend a little bit. By how much? This is going to be the question. Let me take you back and read you one thing that I just skipped. It says here, this section of the ACI requires bars to be extended beyond the calculated distance by the greater of d distance or 12 dB. Say, what is d distance? D is going to be the depth. So yeah, how much is the depth? 18 inch. So it's going to be either 18 inch or 12 times what bar size is? Number 7. So let's say about 12 inches. If I consider this to be number 8, it means 12 or 18. I know that the depth D is going to be controlling my values. It's going to be 18 inches, and this is what I need to use. Therefore, I need to extend this rebar from this point by about 18 inches. And here what it says. The bars should be extended 18 inch beyond the 6.93. What is the 6.93? I'm going to say is going to be X1 value, 6.93 feet. It's going to be like this. This is going to be X1. Beyond that, you extend it by 18 inches. So let me take here 18 divided by 12 is going to be 1.5 feet, plus 693 is going to be 843. I'm going to say maybe about 8.5. Therefore, the length from this point, right, to this end is going to be a good number that I can use in my design. Is going to be 8.5 feet. Any questions? Repeat. Yes? No? We're good?
Could you please repeat?
What's that?
Could you please repeat?
Confirm what? Say it again, please. I can't hear you well.
Could you please repeat the whole thing? I'm a little confused.
Sure.
Thank you.
Absolutely. Is this a good starting point?
Yes.
Begin with this example?
Mhm.
Okay. All right, good. So in this example, it says that you need some number 7 bars. And they give you some information, basic information about the problem. 15 inch for the depth, and they give you this section is given to you, right? And say the amount of AS needed is going to be the same as the amount AS provided. Your demand is exactly equal to capacity. When you look here at this beam, look at this moment diagram, this is what you call here demand. This is going to be M sub U, correct? Jerry, are you with me?
Yes.
I want you please to stay with me.
Okay.
So this is going to be your demand. But if you decide here to provide this 6 rebars, and there's going to be all straight from the beginning to the end, this is going to be your capacity diagram. Let me know if this is clear or not.
So the whole curve is the demand.
The curve,
right?
yeah. This solid curve, the black one, is going to be the
And then
demand.
the box is the capacity.
The capacity is going to be just straight because it doesn't drop. If I just keep all the rebars straight from end to end.
Okay.
Correct? Yeah? All right,
Mhm.
good. Because I have 6 rebars, I can come here and divide this capacity because, you know, capacity is the same as the demand. I just throw this number 300 kfoot just for sake of our discussion. Nothing more. But this number doesn't make, I mean, it's not really needed. I can work without it. So the capacity here box, I can divide into 6 segments. The height of each one is going to be equal to 1/6 of the total capacity. If the capacity is the same as demand to be 300 kfoot, you just take 300 divided by 6 is going to be equal to 50. So each one of this segment or each rebar would be giving you 50 kfoot. That's it. And instead of keeping the rebars from the beginning to the end, I decide here to start to curtail them, which means 2 rebars going to be like this, 2 rebars going to be like this, and 2 rebars going to be like this. So when you count number of rebars at the maximum point of moment, you're going to have 2, 2, and 2. You have total of 6. So if you cut a section right here, you have total of 6 bars. 1, 2, 3 times 2. When you cut a section right here, how many rebars do you have? I need help? Yes?
Would it be 8?
It's going to be 2 and 2. Each one of this line represents 2 rebars, right? 2 rebars right here. 2 rebars give you right here. 2 rebars give you right. I have total of 6. So this line here means 2 rebars, right? Why 2 rebars? Look at this. It's going to be number 6 and 5. It's going to be this one and this one. 2 rebars. The one which is right below it, another 2 rebars. All the way at the bottom, I'm going to have also additional 2 rebars. So I have total of 6. Here is 2, 2, and 2. The bottom 2 is going to be running from the beginning to the end. The second 2 is going to be running from this point to that point. Why? Because beyond that, I don't really need it. I just, what I need is going to be 2 rebars. So in here, how many rebars do I need? I'm going to say, well, look at the moment diagram. I can do it this way. So I don't really need the top number 6 and number 5 rebars. So here I can live with 4 rebars. See, how about here? How many rebars do I need? You see in here, look, I don't need number 6, I don't need number 5, I need number 4, I need number 3. I just need a couple of rebars. Yeah, and look at this diagram. Capacity can be all the way to here, demand is going to be much lower. So I'm going to have here 3 sets of rebars, 2, 2, and 2. Cherry, are you okay with this?
I'm sorry. How do you get 2, 2, and 2? I'm not understanding the 2, 2, and 2.
Okay. You see the 6 rebars, right?
Yes.
All right. How many rebars do you have from here to there?
2,
Good. All right. How about here?
2, and
2.
2.
All right. How about here? I just draw additional 2 here. So you have
There's
6
2.
rebars, right?
Yes.
Your capacity line is right here. If you just keep all rebars, it's going to be running across, right?
Right.
The capacity line is going to be here. So what I'm trying to do is to start to curtail the rebars, which means cut them off at certain locations. Because my feeling is, why should I provide 6 rebars for the entire beam? If the demand is not 300 across, the demand here 300, this is true, and the capacity 300. But the demand here is going to be 200, correct?
Yes.
And the demand here is
It's
100.
100.
So I can start to stop some of these rebars. So what I decided to do is to stop 2 rebars here. You see, I'm going to have 2 rebars in the middle. And the other 2 rebars is going to be this 2 rebars, right? It's going to be from here to there. And the last 2 rebars is going to be all the way from the beginning to the end. So when you look here in the middle, you're going to say, I have 2 and 2 and 2, I have total of 6. When you look at this section here, I'm going to say I have only 2 and 2, right?
Okay.
And then at the end, you're going to say I have here only 2. Does it make sense now? Or
How do you know where to place your horizontal line for the
this
2,
one,
2, and
location?
2? Yeah,
Location?
how do you know where to put it?
All of the 3 bars, they all happen here. You see this? They all at the bottom, but I need to show them different location. Otherwise, I'm just going to be showing you something like this. You're not going to see them, right?
Mhm.
So the location, the vertical location here from the datum, just for illustration. But reality
Okay.
is all of these 3 bars, they happen in one line. They're going to be covering
Okay.
each other out.
Got it.
Make sense now?
Yes.
Yeah.
Thank you.
So this location, no problem. This location is just for illustration. Right? This way I can just bring him up, bring him down. I don't care because
Mhm.
just this is just the length of the rebar. I need to illustrate it somehow.
Okay. Thank you.
No problem. So location of this x1 and x2 is going to be based on the fact that my diagram is going to be secondary parabola. And I should be able to solve it with this equation. So this distance x1 is 693. I need to add 18 inch to it. Why 18 inch? Because it could be the maximum of the two. 12 dB versus 18 inches, the depth of the beam. So, okay. I'm going to be adding here 18 inch to the 693 is going to be 8.5 feet. I'm going to say the first 2 rebars here is going to be at 6.5 feet. How about the second set of rebars? Where should I stop? I'm going to say this is going to be the second set of rebars, right? It's going to be this x2. Now, x2, I'm going to be using the same equation. I'm going to say x2 divided by 12 feet squared is going to be equal to y2, which means 4 rebars. But if you like, you can call this 200 divided by 300. This would be okay. And with that, this distance is 9.8. So the distance from here to there, right, is going to be 9.8. How much do you need to add to it? The same 18 inches. You need to extend a little bit. So I can't really stop it right here. I need to extend it slightly by 1.5 foot. So once I do this, right? So here's the x2, which is this number here, right? So I'm going to be adding 1.5 feet to it. I'm going to end up with 11.3 feet. It's almost like 12. So actually, I don't need this x2 point. If it is 11.3 versus 12, means this rebar is almost here. So I mean, it is not worth it. I may decide my design just to extend it, you know. And then at the end, at the bottom, we're gonna have 2 rebars straight. So total rebars, I'm gonna say here I have A2, and here I'm gonna have 2 rebars, and here I'm gonna have here 2 rebars. Total in the middle, I'm gonna have 2, 2, and 2 is gonna be 6. In this location, once I stop this one, I'm gonna have 4, and this 4 is just gonna be continuous. In reality, all of the 3 bars is giving the top of each other. It's gonna be hiding each other because it's gonna be one line, one row, right? So only for illustration, I'm showing it this way, but in reality, it's gonna be all in one line. So what the code says, if you like to stop some of the three bars, you do either one of the two. And of course, I'm going to be taking the greater of the two. One of them is to do this process. You find out where do you want to stop it, which means at which point you don't really need this three bar. And the other method is to compare this length with L sub D. L sub D, the one that we're just working on. So this 9.8, I'm going to compare it here with L sub D. If L sub D is greater than 9.8, I'm going to be using it. Otherwise, 9.8 should be enough. I said, okay. Let me try here to find out L sub D. So I'm going to do here L sub D for this beam based on this given information, which is giving one exercise. We all went through it a couple of times before. So I'm going to say, here's the last slide. Just do L sub D between here, 1/2 of the slide 16 and the rest of the slide. Can end up with L sub D equals 26.5. So your L sub D is only 26.5 inches, like 2.5 feet. But based on the need of the rebar for the maximum moment from here, I need 8.5. Now, which one controls? I'm going to say I will provide the 8.5. And this gives me the solution to my problem here. I'm going to be taking the greater of the two. L sub D and where the rebar is needed based on this diagram. Questions? Questions? All right, you're done for the day. Please type your name as you sign out. And see you this coming Thursday for your midterm too.